thank you very much for this invitation. I'm quite excited to be part of these InVISION Days. We have been, I believe, selected particularly because we are one of the people pioneering a synthetic data approach in this vision space. And that is what we are going to focus on in this talk. Indeed, my name is Wilhelm Klein. I am the CEO of Zetamotion. And today I'm going to walk you through the following agenda. I'm going to just very briefly outline who we are, what we do, and go a bit deeper into contrasting some of the more conventional approaches to machine vision and AI, and contrasting that with a synthetic approach. I'll go a little bit deeper into what kind of approaches are out there, what are some of the advantages and disadvantages, and I'll outline some of the areas of applications or some of the opportunities that arise from the successful application of a synthetic data approach. And finally, I'll go a little bit beyond a direct application working, let's say, with manufacturers and go a little bit into depth about how this can also be integrated with other inspection providers. So let me get started on who we are. This is what would usually anyone be greeted with if we have our first introduction call. This is how we introduce ourselves. Our flagship product is the Spectron platform. As a deep tech startup, this is our main product. It's an AI platform that makes it very easy to deploy, use, and scale automated inspection, and in particular machine vision. And as you can see here, the four key highlights are no more data headaches, which again speaks to the synthetic data approach, easy integration, extremely high levels of accuracy, and the ability to onboard new products and variations at very high speed. Now, this is how I usually introduce us. I always ask anyone, have you tried computer vision yet? And usually people say nowadays, yes, we've tried. And then you ask them, and how did that go? And that's when you get the wry smiles and the wrinkly foreheads, and people go like, oh yeah, you know what? It's actually been quite difficult. And this already speaks to one of the main problems of conventional approaches, because it tends to be quite easy to achieve something like 80% in terms of accuracy, but to push onwards from there is an exponential increase in the most important resources, namely data, time, and manpower. So usually when you look at conventional approaches as they outlined, it looks something like this, right? You require lots of data points, there's a lot of labeling, a lot of retraining, and so on. And you end up with a situation where you have to collect a lot of data, sit down, do a lot of labeling, a lot of curation until you can climb that accuracy mountain, right? And that can be quite tough, right? So how can we solve this problem? One of the main ways how to do that now is the new kid on the block, which is synthetic data, right? So as I said, some of the problems with the conventional way is the requirement for data collection. It can be resource intensive to have this curated data set, and also sometimes that data set can be quite noisy, right? So what are the promises then of the synthetic data approach? The promises are to make things quicker and easier, to make it more cost effective, because you don't have to sit your engineers down for countless hours and do the labeling, to achieve extremely high accuracy, and because of that also a lot of scalability. So how can we do it, right? This is it's a death by PowerPoint slide of ours, which lists some of the ways of how to do synthetic data in detail, right? So one potential way is have a fully procedurally generated data set, which means as everything is done virtually. There's no primary real data that enters the picture, and it's essentially all code-based. Very controllable. You have a lot of ability to very clearly control what is being generated, but the main disadvantage is that realism might be quite low. So if you rely solely on that, your results are probably not going to be ideal. Then there's something like synthetic compositing, where we're combining real-world collected data with synthesis and various different techniques This achieves a lot more realism, but it can be somewhat labor intensive, both on the collection of the primary data and then also on the synthesis, because you do have manual oversight of creating some of these potential defects and so on. We can work with rendered images that would be using engines like Unreal or Unity or Blender or some in-house solutions that some people like us may have developed. Here, the advantage is we have full control over even full 3D objects. And depending on the level of rendering quality, we can achieve really high level of fidelity on extremely realistic synthetic data, but it can be computationally quite heavy because the rendering can take a lot of time and resources, as I'm sure people will appreciate who've done any video rendering, right? And then lately, the latest newest kid on the block would be generative AI. So this is what is especially in the news. Everyone knows about DALL-E, about Midnight Journey. These are tools that can be extremely powerful, are extremely promising, but gaining full control over them can be very challenging as well. Computational power is also one of the risks involved here, but most importantly really is making sure you have no distorted outcomes, that you have truly properly performing models. Can take a lot of time and expertise to get to a point where you have full control over generative AI. Now, all of these can also be combined, of course. You can have different types of pipelines, starting with one or the other, and then combining it with the other approaches. And through that, you can achieve quite a lot of amazing things. And some of the magic of making it happen and succeeding, as it says in the title, is finding the right way of doing this. Now, once you have it, this is essentially what it looks like, right? You for example, start with a single scan of a defect or a finished product, and then you synthesize different variations of what it might also look like, and use that for training and being able to get started quickly, right? As an example of compositing, and what we mean when in that overview it says it depends a lot on what the qualities are on blending. This would be an example, right? We go from very poor blending to better blending. And of course, the more control you have over the processes, the better you can fine tune the synthetic data approach and be quicker in your deployment. Once you have these kind of tools established, you can see a screenshot of just one example here. This would be controlling some surface attributes for one type of product, where you can really fine-tune procedurally what you are generating and what the texture looks like, what might be the gloss or reflectance, the color, and so on can all be defined very well. And as a result, you can get extremely high resolution, extremely realistic output. So here you would see an example generated metal surface that has a coating finish and comes with several scratches, right? These can be very, very close, mapping what you would see in reality, and give you extreme good starting point to start inspecting without the requirement of collecting more than, let's say, a single scan. You can also do a completely simulated POC, essentially. So using some of the latest tools, you can basically not just recreate the product and the surface and the defects and all of the quality parameters that you want. You can also completely simulate the factory setting. So we can completely simulate the setup, including what sensors might be required, what the setting would be, the speed, the scanning, the angles, the lighting. And we can basically already give you a simulated POC that can give you a very good idea of where you might be ending up when you have an automated inspection system in your factory or in your setting. So where does synthetic data shine? What are the cases where it makes particular sense to use this kind of approach? Now, one area would be using cases where there is very limited data available, because you can't you just have such low production runs, or these defects are so rare that it would be virtually impossible to gather the level of data set that would be required to do conventional training, right? Another example would be having non-uniform or noisy products, which have, by the very nature of the way they are being produced, extremely unique features. So here you can see an example of roof shingles that we have been working with. These are composite products made from glass fiber, bitumen, and Grand granules. And anyone who's dabbled in computer vision will look at this and already see the nightmare and the headache they will produce if you try to achieve very high levels of accuracy in assessing, let's say, this here, right, the so-called the paint line that I'm pointing at here, because it's just splotches of paint on sand granules, and every single one of these shingles looks different, and yet we have to inspect at millimeter or sub-millimeter level of accuracy. So here it would be possible to use a conventional approach in principle, but the amount of data required in order to achieve high accuracy is is exorbitant, because there are also different variants, different types of these shingles, and it just becomes a nightmare if you cannot synthesize your data. Another example would be having lots of variants. So this is the case here, and making it doubly difficult, because it's both lots of variants and very unique products. But here's another example. This is from another real-world customer of ours, making these illumination panels that go into some of the nicer aircrafts around there. And most of the airlines like to have their own designs. So these guys are onboarding lots and lots of new designs constantly. And if you follow the conventional approach, usually that requires a retraining, right? Because if you move from, let's say, diamonds to this kind of complex pattern, most systems will freak out and flag everything as potential defects, right? So in the case of these guys, we've successfully helped them convert from manual inspection to fully automated inspection. We've scanned thousands of their panels, hundreds of thousands of potential defects with very, very granular pass-fail criteria and classification requirements, and achieved an extremely high level of accuracy, allowing them to take the data that is being assessed back to the production line and even increase their process or improve their processes and increase their yield significantly. Another possibility opened up by the synthetic data approach is production line saturation, as we call it. So because usually if you want to, let's say, inspect a product at different stages of a production line, you have to go through that cycle over and over again, right? At every single stage, the product will look slightly different, and you have to collect the data again, spend the time labeling, curating, and so on. But if you can cut down on that required time, you can have lots and lots of production line stations, and you can create what some now call the digital passport or digital twinning of the quality parameters of your product as it moves through the production line. And that allows us to do cause and effect analytics, and again, bring that back to the manufacturer and give them more insights on the production health that they would otherwise not have. And with that, again, they can increase their efficiency and ultimately the yield and quality of their products. Now, lastly, what I would like to also outline is that this is not just something that can be applied directly to manufacturers. And with manufacturers, we're happy to integrate at any part of the journey, whether someone is still on the manual inspection, already has some vision gear, or is trying to get AI to work. We're happy to come in anywhere. But we're also very interested in partnerships on helping those who already have extremely sophisticated inspection gear, but are looking for a bit of a head start on how to address some of the challenges that I've outlined, right? So especially when there is non-uniform products or lots of variations, we can act like, I'm not sure if it's still a thing, but back in the day, we had those Intel Inside stickers on the laptops, right? So you can also imagine our Spectron platform acting like an Intel Inside, having Spectron inside, giving some of this synthetic data power to very sophisticated inspection machines, making them smarter and allowing them to join the AI revolution. So that's who we are, as it says here. can be easily integrated at any part of your journey. And I think I'm now landing on roughly 15 minutes, so that should be fitting nicely in the updated timeline. I'd be very happy to take your questions in the Q&A session, but also just yeah, set up a call, reach out. We're very happy to answer any questions.
Okay, thank you. I have one or two questions. Do you think we will still need real data in the future for eye training, or is all done by synthetic data in the future?
No, absolutely. I think real data will still be required. The main difference is the starting point, whether you can get started with very, very little input data or whether you need a lot. So in our case, these guys, for example, right, that I outlined here, when they onboard a new product, what they give us is one pattern file and one real-world scan. That's it. And that's the sufficient for us to adapt the system and give them the full accuracy across all parameters on a given new variant. And as it's said in the overview, a lot of this still has a real image addition. Plus, once you get started, there's always the possibility of collecting more data, right? More real-world data to further refine the results. And lastly, you can never fully simulate and account for the chaos of the real world. There will always be really strange outlier cases that have not been accounted for, and you need a platform that can capture that. So we have explicitly built in mechanisms for human expertise capture. So when something comes up that just nobody has ever seen before, we can alert an operator, and the operator can explain to us, okay, this is a rare case and it happens because of this and that can then feed back into the system, make it available for future workers, and then also for our system.
Okay, thank you. I have one more question from the audience. How long does it take to make synthetic images with specific errors if you do not have any real parts with errors, like when before the production starts or something?
Yeah, that really depends. So if you give us, usually what manufacturers would have is a defect catalog, right, which has some example pictures. And if you give us this kind of input with a few examples, as well as, let's say, one sample, we can have first results for first deployment within 1 or 2 weeks. And then depending on complexity, it might take a little bit more, but within several weeks, we should be deployed. And then for a given new variants, it's, as it says in our promise, 24 hours for a new variant to onboard.